Hi, I'm Flavius Petruca. I'm a software engineer at Sera, and I'm here with my colleague Andrei.
Hi, I'm Andrei Mihai. I'm a ML services engineer. It's a fancy name for a backend Python developer for ML project. And now we'll wait for a few seconds to see also the slide on the projector. Mainly, we work together on MLOps stuff, autoscaling, GPUs.
Yeah, perfect. Let's get started. So I want you to imagine you have an inference API, and everything is going well, traffic is coming, and all of a sudden, bam, it's overloaded and it breaks. And now, all of a sudden, it's 3 a.m., you are on call, and you are half awake trying to solve an issue that is going on inside your cluster. You try to manually scale, and you try to see if restarting your service fixes this. And this talk is about trying to avoid this type of situations. No one wants to get there, right, at 3 a.m. having an on-call. So we're going to hit a few points, and we're going to talk about MLOps for GenAI, a few methods of autoscaling. This is the mechanism that gets rid of those 3 a.m. on-calls, and a few test methods to actually see that autoscaling works inside the cluster. So, as you probably already know, generative AI is a class of machine learning models that produce new content, text, images, video, text code, whatever, by learning the statistical patterns of data sets and sampling from them. And as you already probably know, those are expensive, those require expensive compute, especially a lot of VRAM, 80 gigabyte VRAM, 140 gigabyte VRAM node. So with these hungry models for VRAM, we hit some struggles. How do we scale for millions of users with this type of issues? Well, it's different. A normal, natural instinct is to go to DevOps tools. That's what you are used to going when you hit this type of issues. When you try to scale, you want to go to DevOps tools again. But for GenAI, that doesn't work, because for DevOps, you are used to having stateless microservices, which are CPU-based. You have traffic that is relatively predictable. And so with GenAI, you break all of these assumptions, because your training job, your inference service, those are stateful apps. So you can't just kill a pod mid-generation. Your CPU that you try to scale up, it's different from trying to scale up when you have a GPU that you try to fit into VRAM, and which takes minutes compared to scaling up CPU, which takes a few seconds. Traffic is bursty, it's unpredictable, and you have to switch the mental model for this. And in DevOps, you're trying to scale an application or deploy an application, and you forget about it. But with LM, you are operating pipelines. You have data collection and validation, you have model training and tuning, evaluation and validation, deployment and monitoring, and retraining and drift detection. If you pay close attention to this, this is not just a pipeline, and it's a loop. And we could be talking a lot about each individual aspect of this loop, where MLOps stands in, and you're trying to make MLOps reliable, fast, and observable inside this loop. But we will be focusing on one concept, and that is GPU. Because the GPU is the problem where teams have it difficult to switch from DevOps to MLOps. Classical infrastructure has two primitives, which is CPU and memory. And now AI has added another primitive.
Yeah.
which is GPU. And you could think that is just, oh, another resource that we have to scale up. But it's not that easy because a GPU is not just a GPU. You have a T4 that is 16 gigabytes of VRAM, an A100 which is 80 gigabytes of VRAM. Those are not interchangeable. As trying to pick the wrong one, your workload will not work on this. So if you get a question on how do we scale this, how do we scale our application knowing this? Well, you have to think of what hardware you are on, what workload are you running, and what are your memory footprints. It's basically like switching from a two-dimensional world to a three-dimensional world. Everything still applies, but you still don't have enough of knowledge. So with this new extra dimension comes extra pain points. And that is because, first of all, it's expensive to run. You need a prepaid pool of GPUs, which it's reserved, it's not on demand, and you pay for it even if it's at 3 a.m. and you're sitting idle with that compute. Monitoring is hard because a single number doesn't say how busy your GPU is. And also, again, each model wants its own chip. Workloads are not portable across silicon. The root cause of all these pain points, it's actually GPU autoscaling, which is extremely hard. Well, autoscaling is the right solution to these problems, but alone it's not enough, because autoscaling is reactive and not strategic. You could set a simple threshold and act on it, but that is just a response and it's not a strategy. You could set some rules, like, for example, setting aside 10 GPUs for training, but that is not smart enough. That's not intelligence. You need a better way to adapt. And how do we apply autoscaling? Well, the simplest form is queue-based autoscaling. You have a message queue, which sits in front of your application, and basically, you rely on a single metric. You do not look at metrics from the GPU. So the metric is the queue size. If your queue grows, you scale up. If your queue goes down, you scale down. So this seems fine, right? But it actually has a limit. Because imagine this is just for a single service. What if this queue grows a lot? You scale your application a lot, right? But if this runs inside a cluster, you will take resources from other applications that might need those resources as well. But let's see how do we implement this in Kubernetes. For example, we have Prometheus, which is a metric database, and here is where your application data stays. You define a Prometheus rule, which basically queries Prometheus for that specific metric, which is the queue size. And this is the only number that goes towards the cluster where you have a queue-based horizontal pod autoscaler setup. And that's it. Basically, this QBS, or horizontal pod autoscaler, scales up or down your pods. So again, this is not cluster-wide efficient. This is not what you want to go as your solution, because it doesn't adapt. It's not truly efficient as you would like. And it's simple to set up, but again, this is not enough, and this is the issue that Andrei will tackle on next year. Thank you.
Yes. So maybe you pay attention to one of the slides when Flavius mentioned the core pain point of GPUs. And the core pain point was that it is expensive. And we need to, instead of pay-as-you-go, how you do with CPU and memory, you prepay. You buy at the beginning of the year, you buy, let's say, like 1,000 GPUs, and the goal is to use these GPUs as efficiently as possible to consume them. Any GPU that is staying idle is consuming money. So this is a totally different mindset from the GPUs. And now we will see a little bit how we can fix also this issue with being efficiently, because the user doesn't care about how fast application C or D is moving. If you do development for many years, you know that in the back of each application, in the back end, you have many components. You have many microservices, monolith, modulith, whatever you want to call them, workers that need to be fast. A user don't see only the latency of one of the workers, they see the latency of the entire workflow. And they don't give a care about the latency of each worker. They care about the latency per total. So what you want to do is to have a method that is actually rebalancing. We do a trick, we do a lie here. We try to use autoscaling for a rebalancing method. What means rebalancing is that we have a set of autoscaler, and each autoscaler will actually move GPUs between applications. And it will do this in such a way that per total you have the best latency. And if you have any GPUs that is idle, you put it into the training platform. So for example, here you have like 20 GPUs, and you try to rebalance these 20 GPUs between these applications as good as you can, and what remains go to the platform. And in order to do that, first thing is actually you need to monitor very well your traffic. You need to have some metrics related to latency, start time, end time, errors, latency, and so on and so forth. And you need to have a mechanism to actually calculate the desired state. In Kubernetes, if you know how Kubernetes works, is actually you have the actual state and desired state. Your autoscaler is impacting the desired state, the state that you want on the cluster. And this prediction mechanism that is the core concept of the auto balancer need to calculate properly the desired state. And this predictor has two phases. And how it's working? In the first phase, you ask the question, if I have all the GPUs in the world, what will be the best latency that I can get for each of my components? The best of the best, right? But I don't have all the GPUs in the world, unfortunately. So in the second phase, I need to put in the algorithm the constraints. I know what is the target latency for each component. I know what is the GPU requirement for each component, and I try to do a mechanism to find what is the best distribution of these GPUs among these nodes. This is for optimization. You may expect that this should be AI, right? It can be AI. It can be an LLM for the prediction mechanism. We actually use a very simple constraint graph search. We don't go into detail. It's a plain old graph search algorithm, but you can use also LLMs or any other machine learning algorithm. In the end, what is important is to have a mechanism that, based on the GPU constraints, which means number of GPUs and type of GPUs, based on the target latency to get the desired state of the cluster. And in the end, what you'll have again, a prediction-based autoscaler, horizontal pod autoscaler, which is actually a lie, how I mentioned, because it's not an autoscaler, it's a rebalancer. It's a component that do this algorithm based on the traffic and is computing what is the best distribution of GPUs among all these components. And in the core, what it's doing is actually sending this desired state to the Kubernetes, and Kubernetes via a GPU-aware scheduling is actually knows what GPU to allocate for each node. Now, of course, everything has a pro and con. The pro is that it's proactive compared with reactive, how Flavius mentioned. It means that we don't expect the traffic to grow and then to actually do the auto-scaling. You can have smart mechanism that is rebalancing everything based on the predictions and also redistribute the idle GPUs to the training. As I mentioned, it's job aware, is aware of each type of job in what pipeline is involved, and also is cluster-wide efficiently. And this is the main trick. It is efficient among the entire cluster, not only for one of the applications. Now, great power comes with great configuration. You actually have a tool that is very, very smart, very powerful. You can do a lot with that tool. What is the trick, right? Because there is no free meal. You can't have anything without a cost, and the cost for this very smart rebalancing and auto-scaling is the configuration. You actually need to understand a lot more about how it's working, these configurations, and you need to configure a lot more stuff. And for that, we have an old friend, which is called load testing. There is a preconception that load testing means actually to do a lot of traffic to your application, which is false. Load testing is actually a loop. It's a loop in which you start with an assumption. You do an assumption that this is the optimal configuration. And you start to do the load. Then you observe. You see what happened. We had issues. What was the latency? Then you update the configuration. And this is the tricky part. This is the human creativity in the loop, where you actually start to come with ideas, what configuration can be adapted can actually improve the throughput ratio. Throughput ratio is how much traffic you can serve per unit of computing. In our case, per pod, but you can calculate it per GPU, per node in the cluster, and so on and so forth. So you do this loop many, many times. And at the end, you find an optimal or close to optimal configuration, and you find the throughput ratio that you can serve with per node. Now comes the fun part. We actually need to do the stress test and auto-scaling test. And for that, we have here a very dummy stress test simulator to understand a little bit. So what we need to do, from load test, you draw the conclusion about how much traffic you can serve per pod. You actually configure your auto-scaling, for example, to min replicas and max replica 20, and you send the spike of traffic. And when you send the spike of traffic, now everything will be dead. Everything will be red, the alert will pop up. Side note, you will also test the alerting mechanism that is working. Your client will be very upset, everything will be down. And what you want to see is the self-healing of the cluster. You want to see that there is no situation where you actually get a lot of messages stuck in the queues and everything is blocked, that you get some bugs that restart in a loop the pod. What you want to see is that after 10 minutes, 20 minutes, the cluster is self-healing, is auto-scaling and is able to serve your traffic. Of course, you also test the rate limit and request throttling because you can't serve all the traffic in the world. You have an SLA, and what is above SLA, you just put 4 to 9 status code. You can also test that some of the node pods from your setup will die, and you need to, again, to see that your application is self-healing in case that you have, I don't know, a bug, and you, of course, test in this scenario the readiness and liveness probe. And now there is a test that nobody is doing on the MLOps. You configure the auto-scaling. Everything is scaling properly. Everything is working great. But let's say that you have only a small percentage of traffic increase. You don't want to respawn an armada of pods just to serve that small amount of traffic. So what you actually need to do is to do an intermediary testing. You just scale your application to a traffic that is somewhere between the min and the max. And what you want to see is that what you calculated during the load test is valid during the stress test and auto-scaling test. You want to see that if you calculate it, you can serve, let's say, 10 RPS per pod. If you send the traffic of 155 RPS, you have 16 pods started. This is a real test. You don't want to have all the time only two situations, min replicas or all the replicas. You want to have intermediary replicas. And again, you can play with those scenarios during this kind of intermediary setup. And you can test even that the min replica is valid if you scale to 0. So you need to do all these tests. And in the end, if you remember from the beginning of the presentation, what we want to do first is to avoid the 3 a.m. call. What is working on our case, again, was to understand what is MLOps, that is different from DevOps, to understand the GPU resource, that GPU resource is wild and is exotic, is multi-dimensional resource, to have some smart auto-scaling mechanism, queue-based, which is also working on CPU-based, not only on GPU base, to have let's say, auto-balancing mechanism, because GPUs are expensive and you need to rebalance the GPUs between your cluster, and to do a lot of tests and to do a lot of stress tests and to test your configuration. But again, this was not, it was not about the 3 AM call. This was another, let's say, fake assumption that we did from the beginning. The availability and resilience of the application is only one of the aspects. Again, the main aspect should be and remain using efficiently the GPUs, because GPUs are expensive, are different from CPU, is prepaid, is not pay as you go. And yeah, last but not least, a message from our partner in crime, Cloud Code. And if you have questions, thank you very much.
Thanks.